Hello students! In today's lesson video, the main idea is going to be to have some rules for derivatives, some kind of shortcut rules for basic derivatives, but there's a couple of other things I want to do. First of all, I want to show you how you can graph the derivative of a function on your calculator, and we'll do that with this first example. So I'm going to use the function y equals 3x squared plus x minus 4. Type that into my calculator and use a window -3 to 3 on x and -10 to 10 on y. And then the notation in your calculator for a derivative, it varies from calculator to calculator. So the older calculators have something like this. In deriv, open parentheses, the function, which we can just type y1, comma x, that's our variable, comma x again. And the newer calculators, when you press the in deriv button, you get the notation, the Leibniz notation, d something dx, and the bar, which means evaluated at, and then you evaluate it at x. So I'll show you how that's going to look. Okay, so here's my calculator. I'm in the y equals menu, and I've typed in the function y1. Now we go down to y2. And once we're in here, we go to the math menu. So press the math button. And then you'll notice that choice number 8 is in deriv. So that's for derivative. So we choose that. Now you'll notice that my calculator changed it to the Leibniz notation, but some of you might just see in deriv in your calculators. It depends on how old they are and what model you have. So we're going to put an x in the box there, so we have d something dx. And then the function goes in this space. You could just type it all over again, 3x squared plus x minus 4. But if you don't want to type it all over again, you can find the y1 variable if you press vars, which is variables, and then you go over to yvars, and then you choose function, and then you choose y1. And then lastly, it's going to be x equals x. So if you typed in x equals some number, it would find the derivative at just that number. But what I'm interested in doing is finding the derivative in general, which is going to be a graph. And then I already typed in my window dimensions, -3 to 3 and -10 to 10. So let's take a look. So the blue one, that was the original graph, the parabola. You can see its vertex is somewhere right about here. And then the red one, that's the derivative of it. So I have that already pictured on my slide. I'm going to go ahead and just work with that so I can draw on it. So remember the other day in our lesson when we were talking about the derivative being positive, negative, or 0? So right here at the vertex of the parabola where you have the minimum, that's where you would have a horizontal tangent line. And so the derivative is 0 because the slope of a horizontal line is 0. And notice that the derivative is indeed 0. And then all the points over here on the function would have a tangent line with a negative slope. And those slopes are getting closer to 0. They're going from being fairly steep to not as steep. So what we see on the derivative, the red graph, is that we have negative numbers because of those negative slopes, and those numbers are getting closer to 0. And then on the right side of the function, you have tangent lines with a positive slope, and the lines are getting steeper, so the slopes are getting bigger. So what you see on the derivative is positive values because of those positive slopes, and they're getting bigger. So it all ties together. Okay, let's do this problem. Match the functions a through d with their derivatives 1 through 3 in the figure, and notice that 2 of the functions are going to actually have the same derivative. So we could go in whatever order we want, but a is a parabola and d is a parabola, and we just looked at a parabola, so maybe we'll do those. So notice that the vertex of the parabola would have a horizontal tangent line. That would be the same for either a or d. So right about there, you would have a derivative that equals 0. So we need to see a graph that has a 0. I would say this one. And then notice that you have lines with positive slopes and then lines with negative slopes. So your derivative should look positive and then negative, and that's the same on D as well. So A goes with 1 and D goes with 1. Now let's take a look at B. Because B is a line, it has the same slope the whole time. It looks like the slope is something positive. We don't really know what it is, but it's the same the whole time and it's positive. So look at the graph number 1. It's positive the whole time and it's constant. Oops. Why did I say 1 for the other one? That was 3. Silly me. Were you saying, Mrs. Emmers, that's a 3, not a 1? Okay. Back to B. B goes with 1. There we go. Now clearly it's going to be C and 2, but why? Well, if you look at C, it looks kind of like a cubic graph, and it looks like it has a horizontal tangent line there and a horizontal tangent line there, so you would have a 0 on your derivative there, and the second graph has a 0 there and there. Now you have positive slopes, then you have negative slopes, and then you have positive slopes. So we see something positive, something negative, and something positive. So C goes with 2. Okay, now let's move on. Now before moving on actually, wouldn't you say that graph B might be a linear function like y equals x or something similar? Graph A and D would be a parabola like y equals something involving x squared, and C would be something cubic, so something involving x cubed. And do you notice that the derivative for C is a parabola, so it's something involving x squared? And the derivative for A and D is a line, so it's something involving x. And the derivative for B is just a horizontal line, so it's just some constant. So what happens is each time the derivative has a power that's 1 lower than the original function. Okay, we're going to take a look at another function and the graph of its derivative. So this one is y equals e to the x. So we're going to do it the exact same way, but before we look at the graph on the calculator, just picture y equals e to the x yourself. Exponential growth, something like that. Do you notice that the tangent line slopes are positive the whole time? So the derivative is going to be positive the whole time. Also, the tangent lines are getting steeper, so the slopes are getting bigger. So the derivative is going to be getting bigger each time. So the derivative is positive and getting bigger. Okay, let's go ahead and take a look at this. You can find your e above your divide, or you can do the second function of natural log. So y equals e to the x. And we already have the notation we need for y2, but I'm going to turn it off for a minute and just look at y1. Oops, I didn't get my x in the right place, did I? Try that again. E to the x. There we go. So let's look at that. That's what we were expecting, the graph of y equals e to the x. Now I'm going to turn on the derivative graph as well. So that'll be red. Wow. Did you notice that red graph graphed exactly on top of that blue graph? They are the exact same thing. So what does that tell us? That tells us that the derivative of e to the x is actually e to the x. It equals its own derivative. So this is going to be our first derivative rule. So let's go ahead and start our notes. This is notes number 19. Basic derivative rules. If f of x equals e to the x, then the derivative f prime of x also equals e to the x. That's very unique. It's something about the exponential growth family that doesn't occur in other function families. And if you want to see the other kind of notation for it, I'm sure you do, the Leibniz notation. This just says the derivative of e to the x with respect to x is e to the x. It says it in one statement, so it's a little bit more efficient than the other way, which we have to include the words if and then for. Okay, so that's your first basic derivative rule. So that means from this point on, anytime you need to take the derivative of e to the x, you don't need to use the limit definition. You can just answer e to the x. The next thing we're going to look at are a bunch of polynomial examples and develop the power rule. And if you watched the optional video number 1, you'll remember me going through the process of using the limit definition of derivative to find the derivative of each of these functions. If you didn't watch that video, then I guess you're just going to have to take my word for it. And what we notice, now let me add a little notation in. F of x equals x means the same thing as f of x equals x to the first. And f prime of x equals 1 means the same thing as 1 times x to the 0. So you'll notice the exponent on your function is 1 higher than the exponent on your derivative. And then you'll also notice that there's a number out front that corresponds to the original exponent. So you bring down the original exponent, bring down the 2, and subtract 1 to get the new exponent. Bring down the 3 and subtract 1 to get the new exponent, and so on. So the rule, which we call the power rule, is for f of x equals x to the n power, the derivative f prime of x is n times x to the n minus 1 power. Now the n in there, it's not part of the base. So, for example, if I look at 3x squared, the 3 is not squared. It's only the x that is squared. If I look at 6x to the 5th, the 6 is not to the 5th. It's only the x that's to the 5th. So in our power rule, the n is not raised to the n minus 1. It's just the x that is. And the Leibniz notation that corresponds to that rule looks like this. The derivative of x to the n with respect to x is n times x to the n minus 1. Now you need to know that any kind of real number exponent works with this rule. It doesn't have to be 1 or 2 or 3 or some kind of whole number. So for a couple of examples, one of these has a whole number, one doesn't. Find the derivative f prime of x if f of x equals x to the 87th. Okay, so all we have to do is bring down the 87 and multiply that by x to the 86th. Okay, so anytime you have a problem that uses the basic power rule, you no longer have to use the limit definition of derivative. You can use this shortcut. Hooray! I should have gotten my sound effects ready so we could have a big applause there. This is a good day. Now this one has x to the negative 2.7 power. Remember, it can be any real number power. The same thing happens. So to get the derivative, you bring down the power, and then you subtract 1 to get the new power. If you subtract 1 from negative 2.7, you get negative 3.7. So that's the derivative. Okay, moving on to develop the next rule, looking again at problems 1, 2, and 3 from video 1, where we found the derivative of f of x equals x is just 1. What if it was f of x equals 4 times x? So what if we multiplied the function by 4? I didn't go through all of the proofs of this, but I'm having to save a little time. You end up with 4 times the derivative of f of x. So the derivative of 4x is 4 times, oops, I'm not saying that very well. I should use the other notation. The derivative of 4x with respect to x is 4 times the derivative of x with respect to x. Number 2, we did the derivative of x squared and we got 2x. What if you want the derivative of negative 3 times x squared? You get negative 3 times 2x. So you just multiply that constant by the derivative of the polynomial part. So the derivative of negative 3 times x squared is the same as negative 3 times the derivative of x squared. It's like you could factor out that constant. And number 3 down here is the same. The derivative of x cubed was 3x squared, so the derivative of 10x cubed is just going to be 10 times 3x squared. You just multiply by that constant. That's all you have to do. and that is called the constant multiple rule. So I'm using a for my constant here. If I have f of x equals a times x to the n, then I bring down that n and I multiply it by the constant to give me my derivative, and then of course subtract 1 to get to the new power. And if you want to see that in Leibniz notation, it looks like that. So the new constant is a times n. So let's look at a couple of examples. Find f prime of x if f of x is negative 27 times the square root of x. Okay, so first of all, I would rewrite the square root of x as x to the 1/2 power. So our function is negative 27 times x to the 1/2 power. After doing that, we can use the constant multiple rule and the basic power rule. So what we're going to do is bring down the 1/2 and multiply it by negative 27. And then we have x to the negative 1/2 because we had to subtract 1 to get the new power. Now you don't have to write it out like that. You can just write negative 27 halves. And then the other thing I would do is I would change the notation back to a radical. So x to the negative 1/2 power is the same as 1 over x to the 1/2 power. And changing that back to a radical would be negative 27 over 2 square root x, because x to the 1/2 power is square root x. Okay, let's take a look at number 4. Using Leibniz notation, it says, find the derivative, that's what this part is, of this function, 2/3 z to the 4th, and then it says evaluate it at z equals 2. Well, we do the evaluating last. So let's start with the derivative of 2/3 z to the 4th. Notice I'm using a z instead of an x. It doesn't have to be an x, it can be any letter. And I identify the variable down here on the bottom. So we bring down the 4 and we multiply it by 2/3. And then we raise z to the 1 lower power, so z cubed. We're going to evaluate that at z equals 2. We can simplify it first if we want to. We have 8/3 z cubed. Evaluate it at z equals 2. That means plug in the 2. So we have 8/3 times 2 cubed. 2 cubed is 8, so we have 64/3. Okay, I know that this is a long video. Sometimes that's just the way it is. I don't want to skip over too much and then have you wondering what this stuff is all about. Back to the calculator problem. Remember, this was the first one in today's video. We put the function in, we asked the calculator to graph the derivative for us, but now that we have our new rules, what is the derivative? Oh, there was nothing under that box. I guess we get to figure it out ourselves. Well, let's use the rules that we learned. So the derivative of 3x squared would be 3 times, bring down the 2, and subtract 1 to get the new power. And then, you know what, I haven't talked about this yet, but I guess this is going to lead us to our next rule. We're going to add the derivative of the next term. So the derivative of x, remember that's x to the 1st, bring down the 1, and subtract 1 to get the new power. And then subtract the derivative of 4. The derivative of 4, what would that be? Let's see, if you had y equals 4, and you pictured that on a graph, that's a horizontal line. What is the slope of the tangent line? 0. Okay, here's a shortcut notation. Y prime for the derivative would be 0. So just minus 0. Any constant has a derivative of 0. That should be another rule. I'm going to make a new rule. The derivative of a constant is 0. For example, if f of x equals a is a constant, f prime of x is 0. or the derivative of a with respect to x is 0. Okay, now what I wanted to do after simplifying this here, this is 6x plus 1. I want to graph that, and I want to see if it looks like the graph that the calculator gave us. So back to the calculator, there's the function, and y2 is the derivative, but let's go ahead and type in that derivative, 6x plus 1. Let's see if the black one ends up looking exactly like the red one. Why, yes indeed. If you didn't catch that, it drew the red one and then it drew the black one right on top of it. You can rewind and see it again. So, that's kind of cool. Okay, what are we going to do next? So I wanted to point out actually that you could also have the function y equals 3x squared plus x minus 99, and its derivative would be the exact same thing, 6x plus 1. Or y equals 3x squared plus x plus 1002. And its derivative would be the exact same thing, 6x plus 1. So adding or subtracting those numbers is just shifting the graph up or down, but not changing the shape, so it's not changing the tangent lines at all. Okay, so here's the rule I alluded to earlier. If you want to take the derivative of a function that has multiple terms added or subtracted, you just take the derivative of each individual term separately. So the derivative of f of x plus g of x is just f prime plus g prime. The derivative of f of x minus g of x is just f prime minus g prime, etc. So let's do an example. Find f prime of t if f of t is 6 times the cube root of t plus 1 over the square root of t. So we have a term plus a term, so what we're going to do is take the derivative of the first term and take the derivative of the second term and add those together. But first I'm going to rewrite f of t. Remember that a cube root is a 1/3 power, so we have 6t to the 1/3 power. And remember that a square root is a 1/2 power, but if it's on the bottom we have a negative exponent, so this is t to the negative 1/2 power. So that's just rewriting the function to prepare it for differentiation. Differentiation means finding the derivative. So now let's use our rules. On the first term we're going to bring down the 1/3 and multiply it by 6. So that gives us 2. And we're going to raise t to the 1 lower power. So 1/3 minus 1 is negative 2/3. Plus, now let's find the derivative of t to the negative 1/2. So we bring down the negative 1/2, and we then subtract 1 to get the new power. So the new power is going to be negative 3/2. Now I would rewrite this with radical notation because the problem was given in radical notation. So if you have a negative exponent, you're going to move it to the bottom. So at this point we have 2 over t to the 2/3, and we also have minus 1 over 2 times t to the 3/2, getting rid of those negative exponents first. Now let's change our notation into radical notation. If you have a cube root, if you have a 1/3 power, it's a cube root. So we have 2 over the cube root of t squared. And then if you have a square root, it's a 1/2 power. So we have 1 over 2 times the square root of t cubed. Now you could also simplify the square root of t cubed by factoring out a t. So for our final answer, 2 over the cube root of t squared minus 1 over 2t square root t. Now that problem was like 1 part calculus and 4 parts algebra. And that's something that you're going to realize as we go further into this class. There's a lot of algebra. You might understand the calculus backwards and forwards, but then the algebra is what often trips us up. That's just kind of the way it is. Okay, here's your assignment. Thanks, everybody.